The introduction of solar and wind energy is turning electricity markets upside down. Their low operating costs and varying output levels are changing market fundamentals, in addition to reducing pollution from the power sector. So let's take a closer look at how the introduction of renewable energy sources affects electricity market prices. Then we can also review the consequences for investment. Let's start with a traditional load duration curve. The curve shows the peak demand on the left. The lowest point on the right represents the lowest level of electricity consumption. Three technologies in this simplified market are used to serve demand. Coal is used for base load because its average cost is lowest if it runs many hours. Efficient gas turbines, combined cycle gas turbines, are used for medium load, and the open cycle gas turbines with their high fuel cost but low capital cost are only used during peak hours. We call them dispatchable generators because unlike solar and wind energy, they can always be dispatched. We control when they operate. In the future, other technologies, for instance hydrogen or ammonia storage plants, will need to take their place. Now, how does the dispatch of these plants change when you introduce a lot of solar and wind energy? When there's a lot of wind and solar in the energy mix, the effects depend on the weather, as you can see from this graph. The red line shows the demand curve. So the gray area underneath it is the total demand that must be satisfied at any time. Blue is wind generation and yellow is solar. What remains after we subtract solar and wind energy from demand is called the residual load. This load has to be served with dispatchable generation sources. In this example, the combination of solar and wind sometimes adds up to more than the demand for power. So then there's no need for dispatchable generators, such as gas plant, to run. In other hours, however, there's not much supply of solar and wind generation, and the demand for power has to be met largely or totally by conventional sources. Now what happens to the load duration curve? The black line shows the load duration curve that we saw before. The red line shows the residual load curve, so the load minus the supply of solar and wind energy. When there's no sun and no wind and demand is at its peak, the residual load is pretty much the same as full load. In the graph, the peak of the residual load curve, in red, is almost the same as the peak of the original load curve, the black curve. Regardless of how much solar and wind capacity is built, there will always be times when they do not produce enough to meet demand. However, during other hours with peak demand, there is solar and or wind energy, so the red residual load curve drops faster than the original load curve. Of course, there are also many hours per year when there's a lot of solar and wind generation. During these hours, the residual load curve is low. The residual load duration curve shows that the share of coal now in the optimal portfolio is smaller, and the relative shares of combined cycle gas turbines and open cycle gas turbines have increased. This can be understood intuitively. With solar and wind energy providing part of demand, the demand for dispatchable capacity becomes more peaky because it needs to produce less energy, but we still need it to serve the same peak capacity. If there really is a large supply of renewable energy, there may even be a surplus of electricity. So we don't need any conventional power generation at all during these hours. This happens in Denmark already. So what happens to the red line if there's a surplus of renewable energy? Then the residual load duration curve crosses the x-axis at a level lower than the total number of hours per year. In other words, there will be periods when the residual load is negative. Now we don't need any baseload plants anymore, and the total amount of energy that has to be provided by the dispatchable plants has decreased again. So what is the effect of solar and wind power on the power system? They reduce the volume of energy that needs to be provided by conventional power, but they may not reduce the volume of installed capacity that is needed to meet the peak demand in the year by much. Please note that this latter effect depends on the location. In warm, sunny locations, solar power will contribute more to peak demand than where I live in the Netherlands. So what does this do for the investment incentive? Let's take a look at the price duration curve. At times when there's much solar and wind generation, the power price goes down. So During peak demand hours with much renewable energy supply, peak prices become normal prices. During mid-load and off-peak hours, wind and solar will also push prices down. Some hours, the electricity price may even go to zero, indicating that the marginal cost of electricity at that time is zero. However, the capital cost of the generation portfolio does not go down. We still need more or less the same volume of installed dispatchable generation capacity. So if these power plants run fewer hours, their revenues would have to go up during these hours to recover their costs. Will this really happen? In theory, it should, because the market should find a new investment equilibrium. With a bit less dispatchable generation capacity, peak prices should increase up to the point that the remaining dispatchable plants recover their costs. The increase in peak prices could, in the long run, be very high, making this very unattractive for consumers. However, given that we have enough power plants already in the market, we are not seeing an increase in peak prices right now. The result is a lot of uncertainty for power producers. So this is the question. We still need more or less the same volume of dispatchable capacity, but it is entirely unclear whether market prices will be high enough to support this. How are we going to finance that? It's true that we will need to phase out fossil fuel plants, but the replacements like biomass or hydrogen storage facilities will have similar cost characteristics or maybe even more expensive. Consequently, the question of how to meet residual load in a renewable energy system is becoming a key challenge.